Hey there. So in this video, we're going to be going over and kind of taking a deeper look at springs and kind of what's energy stored in them, how do springs work, kind of some fundamentals of springs. And so the first thing really is that a spring is just some elastic object that stores mechanical energy. Now, this is maybe the first time I've said this kind of phrase, this mechanical energy thing here. And all mechanical energy is it is the combination of potential energy that could be potential due to gravity or potential due to a spring plus the kinetic energy. That's really all mechanical is. It's just the combination of both these energies, potential and kinetic. It's just kind of a shorter way to say that. And so that's what we have right here. Mechanical energy is the total of potential energy plus kinetic energy. It's just a way of saying all that it has that we can kind of get back essentially. And so most often we talk about, well, a spring is maybe the little thing that's in your pen, right? You disassemble, it's this little coiled thing. So steel springs are a very common one. That's what AP Physics uses a lot on questions and such. But also rubber bands. You could even talk about like a kitchen sponge is something that's kind of springy, right? There's lots of different examples. I actually have a video here that kind of shows a couple that's pretty great. These exercise balls, right? So maybe you see these exercise balls and you go, oh, this would be funny to go and run at someone else. Well, they store a lot of energy in them, right? The moment that they kind of compress together, they're like a spring, and this person just got blasted, right? And so these yoga balls, you can just find lots of videos of these all over the place, are a great example of springs, actually. And so what I want to look at here is just kind of a generic steel spring. So just draw some little kind of coiled thing. It doesn't need to be perfectly like this. Usually I kind of just curly cue mine, something like that when I draw my springs. And without pushing or pulling on it, we're just going to say that it's at equilibrium. So wherever the end of your spring is, I just kind of have this purple dash line. That's just kind of the equilibrium position of it, just kind of relaxed at rest. Then, if you were to push on this first spring, you push it, so you're compressing it together, you are doing work, right? Like you are using some of your energy, you're exerting a force over some distance that you're actually squishing the thing. And so now it is in this compressed state. And when it's in this compressed state, now the spring is actually going to start fighting back. It's actually kind of resisting you. And oddly enough, even though we said that work is force times distance, where we used a d for it, when we talk about springs, we'll actually call this distance x. But please do know that they really are both the same exact thing. They seriously are. And so now we have it in this kind of compressed state. Or you could do the opposite, and you could have this spring at equilibrium, and then you grab and you start stretching it. So you're still acting a force, but now you're forcing kind of in the opposite direction over some other distance. So you could stretch the thing here, and this is when it is extended. And so now my spring is still stretched the same distance x, but one was kind of a compressed version, one was an extended version, but they both have been kind of stretched or compressed the same distance. So this kind of x is the same, or the distance that you moved it is the same. But now we can see that the spring is actually kind of acting now back towards kind of the equilibrium. So in both cases, whether it's extended or compressed, the spring actually wants to kind of act in the direction towards equilibrium. It wants to go back to kind of its natural rest state. So now, what do you think this force of a spring depends on, right? Well, the first thing that I would kind of point out is that, well, you can make the spring out of different things, right? You can make a thin little one like in a ballpoint pen, or you can make it like a really sturdy thing. Who knows? Maybe out of some really strong kind of steel or some other alloy. And so I would say that the first thing that a spring really depends on is how kind of strong the material is. And so we're going to call that this spring constant K. And so a stiffer spring has a larger spring constant, so it would exert a bigger force. So if you have a bigger K value, you're just going to have a bigger, stronger spring, okay? Now, also, and maybe like you've just played with a rubber band or something, or you've played with a spring or on a trampoline or something, the farther that you stretch it, so the bigger this X value is, the more it's going to start fighting back. I actually have this kind of piece of workout equipment called this like Gorilla Bow, and it's essentially like a bow-shaped device with these huge bungees you hook into it. And the farther you stretch it, the more it resists you. And so the second thing that this kind of force for a spring depends on is how far it's stretched. When it's at equilibrium, it's not stretched at all. It's not acting in any direction. You stretch it just a little bit to here, it's going to fight just a little bit. You stretch it way over here, it's going to start fighting a lot more. So the farther you stretch it, the more the force is going to increase. And so we're going to say that, and we kind of have either this direction or this direction. So how do we kind of figure it out or represent that? Well, I would say that it's not just X, but it's the absolute value of X. And it does have a direction, since one is kind of in to the left, one's to the right. So we're going to take kind of the absolute value of this vector that kind of is X, okay? So this is kind of the two things that really depend and affect the force on a spring. And since, again, we're not going to really care about the direction of the stretch or compression, we were taking the absolute value, we're going to make this the absolute value of the spring force. And this is the exact version of the equation on your AP equation sheet, actually. This is the exact same equation and the exact same format. So a spring depends on how stiff, or the force of a spring depends on how stiff the spring is, and it depends on how far it is stretched or compressed. All right. Now, what I wanted to do actually is just kind of draw a little graph here. And I have this graph, and it kind of shows, oh, well, the force on a spring based on X. We're not going to magically change the material of the spring. We're not going to change the K value. But as I stretch it farther and farther and farther, so as I kind of move in this X direction, the farther I stretch it, the more this force increases, kind of nice and easily and smoothly. That's why we have a nice kind of constant straight line. It just kind of constantly increases. So what I want to do is look at the area of this. Well, we said that this amount X is how far you pushed it, D, right? Or how far you stretched it. Well, the area of this would be the force times the distance, right? Well, isn't force times distance, we just said, work? This is actually from our last kind of topic, our last page that we kind of looked at. So the area of this is the work, which is pretty awesome. So the area is the work. So that means that our work is F times X, which is bizarre. So what that means, which is the same as force times distance. So this means that the work is, underline, is the area of the graph. Well, if I wanted to write the area of this graph, though, it's just a triangle. So I would say that the work is 1/2 the base times the height. But the base is X. So we're going to say 1/2 of the absolute value of X. And then the height is the spring force. So now I just have the spring force. And we do have some absolute values here. I'm just going to drop them in a second just to kind of clean things up. But now we said that we have this equation up here for the spring force. So what I can do is I can substitute this kind of blue equation is for the spring force here. So we're going to rewrite this now and have 1/2 of X. And then I'm going to draw my absolute values just to kind of make it a little cleaner. And then we have K and X. So we can combine this now. We can rewrite this one final time as 1/2 kx squared. And so really, the work that you do to compress or stretch a spring is going to store energy in it. And that energy we call the potential energy of the spring. So U with a little S below it. So the spring potential energy. And that's 1/2 kx squared. And so maybe you're going, why don't we just call this the work? Well, it's no longer you pushing it and acting upon it. This is now, it's just in this compressed state, or it's in this stretch state, and you're not like really pushing anymore on you, maybe you just clip it and you're just kind of, you put a little wall here or some little stop so now it doesn't push out. Well, that energy is just stored. How much energy is stored? Well, the energy that's stored is based on the spring constant and how far it's been compressed or stretched squared. Okay. And now we have this little activity. And we would normally do this in the classroom, but we're not in the classroom. And so I have this hook in my ceiling. And from the hook, I have this spring, and it's a giant spring actually. And I have a bowling ball. And I drilled a hole in the bowling ball and I put a little eye hook. So an eye hook is kind of like a little screw. So it has all these little threads on it. And then it just has a little eye shape, kind of a little eyelet there. And so what I can do is I can hook the bowling ball to the spring. And when the bowling ball is hooked on the spring and we have the mass, I put it on a scale so we know the mass of my bowling ball. What happens is, well, now the bowling ball is pulling down on the spring, so it stretches it. So we have some distance x that it has been compressed or stretched. In this case, it's been stretched. And so at some point, though, the bowling ball is just going to be kind of floating. It's not going to be bouncing. It's not going to be continually falling towards the floor. What happens is it's just staying still. It's doing a whole lot of nothing. And so what that means is that the force of gravity pulling down and the spring force pulling up must be balanced. They must be equal but opposite forces. And so what I want us to do is we want to find the spring constant for the spring that's suspending the bowling ball up in the air. So we know how far it is, the spring is, how long it is when it's kind of relaxed, when it's at equilibrium. And I went and I measured the total distance. This is actually like from here all the way down to here. So I measured how far it is when it's stretched. And so with those two, if I subtract, I could find the difference. The difference would be my x value, how far it is actually stretched, which is 20.4 centimeters. But we need this in meters. Meters is kind of our standard units. So I need to use 0.204 meters. So now, how the heck do we find the spring constant? Well, we know that these two forces are equal, and we know the mass, and we know g, and we know x, so we should be able to just set these forces equal and plug in. So I'm going to say that my spring force is equal to my force of gravity, and I should really have absolute value bars here because one is up and one is down. But then we can plug in and say that kx is equal to mg. I'm going to slide this up just to give myself a little more space. So kx is equal to mg. So now getting k alone, our spring constant is equal to the mass of the bowling ball times g divided by how far the spring has been stretched. And now plugging into that, I get that I have my bowling ball's mass of 5.1715 kilograms times our 9.8 meters per second squared. That's our gravitational acceleration divided by this 0.204. That's how far the spring actually stretched or had to stretch to balance out and fully resist gravity here. And so in the end, I put this all into my calculator and I get 248. And now this is kind of the weird part. What the heck are the units? I would strongly say that, well, I see meters up top, meters on bottom, those should cancel. But because we're talking about a spring and it's acting with some force the more you squish it or the more you stretch it, I would like to introduce that if we look at the stuff on top, we have a force essentially, right? We have a force up here on top. And so we have a force that's in newtons divided by meters. So we're going to say this is Newton meters. That's actually the unit for spring constant because for every meter I squish it, this is how many newtons it's going to resist. Or for every meter I stretch it, how many newtons it's going to resist. Now, I want to look at this one more time. And I have a black bowling ball. And the black bowling ball is much heavier. So here's the new mass. Here was the old mass. And so we can see it's significantly heavier. And what I want to do is find the spring constant again. And I want you to pause for a second and think about, should this spring constant change if I put a different bowling ball on it? Quite frankly, no. The spring isn't changing. You're not making the spring out of a different material. Remember that this K is that tensile strength. It's kind of a property of the spring itself and what it is made of. So we should actually still get the same 248 newtons per meter by putting on a heavier bowling ball. Well, how does that happen? Well, the spring is going to have to stretch more. We're going to have a bigger X because we have a bigger M is what really should be happening here. And so I went and I actually measured it, and I got that the stretch length, so X stretch, is 50.65 centimeters. So that gives me, if I know the relaxed length is this and the stretch length is this, subtracting those two will give me my actual X value. So my X equals 24.46 centimeters. And we need to put that in meters because, again, our units have to agree, just like how we have meters kind of up above here. All of our units have to agree. So I have a 0.2446 meters. So now we know the mass, we know the X, so we can literally just plug back into the same thing. I would encourage you, if you're like, I need to rewrite it, totally rewrite it. Go ahead and say like, oh, well, the forces must balance. Force of spring equals force of gravity. That means I can rewrite it as Kx equals mg. Then I can go ahead, I can get K alone. K, our spring constant, is equal to the mass of gravity over how far it's stretched. Plugging into that, we then end up having our 6.1970 kilograms. That's the mass of our bowling ball times the acceleration due to gravity over this new stretch length. And when I put that into my calculator, I got 248 newtons per meter still. So this does check out. We do have a bigger mass, but we do have a bigger X, such that these two forces still balance each other out. And so the property of the spring itself is not changing. Thank you so much for watching. Let me know if you have any questions.